Okay, so we took a test on Monday, April 27th, and it was on the AP Classroom website. It was no calculator, multiple choice. Um, I just went through and looked at which questions did we miss the most, and I'm going to do a video here working through those solutions. If I need to, I'll cut it off and do a second video because I have a 15-minute time cap, so we'll see kind of how that process goes. In each one, I've denoted the number, except for this first one, it didn't get put through correctly when I cut and paste. So that's number 3. In this first one, let's just get right to it. We've got a particle moving along a straight line. The graph of the particle's position, x of t, is shown. We have horizontal tangents at 1 and at 5. So here and here, our slope is 0. And we've got a point of inflection at 2. So here's my inflection point. And for what values is the velocity increasing? So we want to know where the velocity is increasing. So we've got position, they're calling x. We've got velocity, and then we have acceleration. And these three are tied to each other, each one being the derivative of the one that comes before it. And we want to know where velocity is increasing, so we want to know where its slope is positive. So we're looking to figure out where acceleration is positive. So acceleration is the second derivative of position, meaning to figure out where it's positive on a graph of the position function means we're looking for concavity. So we're trying to see where this thing is concave up. And it is concave up from 0 to the inflection point, which happens at 2. And that's it. So there's nothing really more to do on this problem. There's no computation of any sort. It's just a kind of a big picture thinking about how these three things are related to each other. So the first one should be letter A. Second question, question 6. What is the area of the region between the graph y equals x squared and y equals negative x from 0 to 2? So y equals x squared is parabola, and y equals negative x looks like, let's see, like a linear function. I know we don't actually overlap right there. I just got a little sloppy. But we're going from 0 to 2, so even though my picture is not great, we're good. So 0 to 2. And you've got this space, you've got this space. A couple ways we can do it. I think probably the easiest way is just a straight integral. So integrate 0 to 2, top minus bottom. And my guess is maybe the minus and negative triggered some mistakes, but that's going to be a plus. And we're going to integrate from 0 to 2, so we have x cubed over 3, plus it'd be x squared over 2, 0 to 2. 0 is not going to produce anything, so I don't need to worry about it. 2 goes in, I've got 8/3 plus 4/2, and then I'll write it. I mean, I don't need to, but it'd be 0 plus 0 when the 0 goes in. So 8/3 and then 4 over 2 is, of course, a 2. So I've got 8/3 plus 2. Well, 8/3, let's say 8/3 plus 2. That's 8/3 plus 6/3, which is 14/3, and so our answer would be D. And that's it for question 6. Pretty straightforward question. I'm guessing probably the minus and negatives where we got thrown. Question 9 is a little less straightforward. So we've got a piecewise function, and they're saying the function is defined above with c and d being constants. So think about those as just numbers. We don't know what they are. If f is differentiable at x equals 2, what is the value of c plus d? This is an interesting way to phrase it. What it means is we don't necessarily need to know either c or d on its own. We only need to know the combination of the two. And I have a feeling, I haven't run these through in advance of this video, so I have a feeling that's going to come into play. But let's see, if we're differentiable at 2, if I were to take the derivative of the left-hand piece, so that's this piece, that derivative, or that f prime, is c. And if I take the derivative of the right-hand piece, so we'll do 2 stars, there's 1 star, there's 2 stars, that derivative is going to be 2x minus c. And we're evaluating specifically at x equals 2. So I'll plug in a value of 2. So 2 times 2, that's 4 minus c. So those two derivatives for this thing to be differentiable have to equal each other. So let's see, 4 equals 2c, and then c would be 2. I don't know what d is yet, but we can go get that. And actually, my thought process on this in the beginning is off now because we actually know what one of them is. So I know my c is 2. And sure enough, they were nice and fun for us, and they gave us 2 as a potential answer, which it could be if d was 0, I guess. I don't know if that's the case. We'll have to go find it. But in order to find it, I'm going to grab a different colored pen here because I can. I now know C is 2. So that means this first part, this left part of the single star, is 2x plus d. Oh, that's a terrible d, almost as if that was an ion. 2x plus d, there we go. And then the right part would be, what would that be? X squared minus 2x. Those two things then need to equal each other. So that's just, again, all I did was take 2 and plug it in for C on both those. The function, there can't be a jump in the function. So the left-hand side has to equal the right-hand side. They have to touch each other at that same spot. And so, again, absent an x value, it's a little trickier to solve. But with the x value, you just put a 2 in there. So there's 2 times 2, that's 4. 2 squared is 4. And then minus 2 times 2. So it'd be 4 plus d equals 4 minus 4, which is 0. So d equals negative 4. So then I've got d is negative 4. I've got c is 2. And look at that. They put the negative 4 in there just for fun as well. They threw a 0 in as a common mistake people might choose. 4 just kind of seems like a fun one they chucked in. I don't see how that one's linking to these numbers. But these other 3 are just common errors you could pick. But then they're looking for c plus d. So we're going to add these two things together. And that's going to give us negative 2, which is the answer. So that one's number 9. Question 22 is a really good question. The common mistake you all made, we'll see as we go through it. If you take the derivative of an integral, it knocks out the integral sign. So you would get sine of top bound being plugged in. Oh, that's a squared, right? X squared cubed. So it's sine of x to the 6th. That's the common mistake. So the integral knocks out the derivative. Those offset each other. Top bound gets plugged in. And you end up getting this sine x to the 6th, which is the most common mistake that people would choose here would have been C. You also have to multiply by the derivative of the inside. And you have to be a little bit creative. I remember a long time ago when we did this in class, we talked about how you have to creatively understand that this is the inside. So when you're applying the chain rule, when you take a derivative, you need to also multiply by the derivative of the inside, which is 2x. So we need to multiply by 2x, and that gets us answer E. And you can see all these different derivations on the problem. You've got sine of x cubed. That's if you forgot to plug in x squared. You've got 2x if you remembered chain rule, but then sine of x cubed if you forgot to plug that in. And then they threw in the cosine just for fun, because if you take the derivative, of course, or antiderivative of sine, you get negative cosine. But in this case, we're taking the derivative of an integral. They knock each other out, and we just have to account for the inside. So we get letter E for this one. Question 23 is also looking at areas. So we're saying from 1 to 10, the area under F is 4. From 10 to 3, the area is 7. That is tricky because they reverse the bounds. Those tricky AP people. So let's see. Just for fun, I'm going to reverse them back. So 3 to 10. If I pop the bounds the other direction, all that does is means I'm reading the other way, so I get a negative 7. And then 1 to 3, well, if we want, here's the two pieces that would need to be added together. So I don't know what this is. I'll put a question mark there. I need to combine that to negative 7 to get 4. So the thing that combines to negative 7 to get 4 is 11. And there really isn't any computational work required on this one. That is it. Yeah, I'm trying to think. I just can't think of another way to break it apart. I suppose you could do something like subtract this integral. Yeah, I think this is the cleanest way to do it. Just get the bounds all facing the same way with the negative sign. Understand that you're combining these two. And then just look at your options. You only got 5 choices. So what, when you combine it with negative 7, is going to get you a 4. You really don't have to do a ton more than that. So that's question 23. Question 24, if f prime, capital F prime, is a continuous function for all real x, and we've got this thing. Oh, that looks goofy. Look at this thing. 8a plus h f prime dx, h going to 0, 1 over h. That is just a ton of symbols. So if f prime is a continuous function, then we've got to evaluate this limit. Well, that's fun. Well, let's see. Not sure what else to do, so I'm going to start just by trying to make it small. I'm going to start with a piece that maybe I can do something with. So if I integrate f prime, when you integrate f prime, you get f. So you integrate a derivative, they knock each other out. Kind of a big theme of calculus, right? That an integral and a derivative are reverse processes. I then need to plug in the endpoints. So there's a and there's a plus h. So I've got f of a plus h minus f of a, and that's the top, or the numerator. And let's see, I'm going to bring back in this 1 over h piece that's just kind of hanging out over here. So if I've got 1 over h and I multiply by that, there's my h on the bottom, or multiplying by 1 over h, and then I've got this limit out front. And if this doesn't look familiar to you, you're gonna see it revisited in the last couple of problems here. I think the last problem. This is the definition for a derivative. This is way back in September. This is what it means to be a derivative. Technically, this h can be written as a plus h minus a. So we've got rise on top, change in y values, run on the bottom. So here's the run, but we just do a minus a and get rid of it to simplify the expression. So this is the definition of a derivative evaluated at a. There's really no mechanics required on this one other than just sight recognition that this is a derivative evaluated at a. It's a really tricky way to word it. I like it. It's definitely what the AP forces you to think about definitions this way. Okay, so we've got 2 to go. I think I can wrap it up in one video, which I'm not usually brief, but I think we can get it done. Question 30 was limit as x approaches 3 of f of x is 7. Which of the following must be true? So let's see, f is continuous at 3. F is differentiable at 3. F of 3 is equal to 7. For sure, this last one I can chuck out. I'm confident that one can go away. A limit, a limit's just what happens when you get close. In other words, there can be a hole there. You don't actually have to have the function defined at that spot for the limit exists. So that one right away jumps out at me as, hey, this probably isn't necessary. It does not have to be true. It could be true, but it does not have to be. Let's see, let's try differentiable next. So do we have to be differentiable at 3 for a limit to exist? We definitely don't, because if you think about like an absolute value spike or a cusp, that could be the spot you have where you're approaching the same value from the left and from the right. So the limit exists, the limit's sitting down there happy and existent, but the derivative does not exist. So there the derivative doesn't exist. So that's an example or a counterexample. So it does not have to be true. And then to have continuity at x equals 3, that one for sure is not true. Because you could be happily moving along on a curve, have a little dot right here. And let's see, you could be happily moving along on the curve, then you got boom, boom, and you've got a removable discontinuity. The limit exists, removable discontinuity. We've removed a piece, it's this floating point up here. And we've got function defined everywhere else. So the limit is existing, we're moving from the left and the right to the same location. So we don't actually have to be continuous either. And this is one of those rare situations where the answer is none. Kind of cool. So process of elimination, going through and coming up with counterexamples for each of these is a good process here. And that takes us to the last one, which I've got a little over a minute left on this video. I can get it done with. You should look at this thing and you should think, my gosh, we just talked about this. This is the definition of a limit. Of a derivative, sorry, I misspoke, I was getting so excited. The definition of a derivative is limit as h approaches 0, f of x plus h minus f of x all over h. And then you can put a's in there instead of x's, sometimes they do that. So in this case, they're asking you to take the derivative evaluated at 3x. So that's our input value. Take the derivative and evaluate it at 3x. We'll take the derivative of tangent. So f of 3x. So take the derivative of tangent. Well, the derivative of tangent is secant squared, leave the inside alone, times by the derivative of the inside is 3. And there we've got our answer right here. And the answer on that one ends up being B.